Thank you for watching my video. My name is Astrid Krasniqi. Today we will be learning about CCNA Semester 2, Day 1. On this lesson we'll talk about routing and switching, Day 1. Part 1 is divided in two parts. We have Part 1 and Part 2. Part 1 talks only about introduction to switched network. On this lesson we'll talk about hierarchy in the borderless switched network. Then different kind of form factors that we have for the switches, the way the switches they forward the frames. Then we learn how dynamically the switches populate the MAC address table. Then we learn about switching forwarding methods. Then the last section of this lesson is different way we learn about collision domains and broadcast domains. Okay, so let's get started. Part 1, introduction to a switched network. Okay, on this screen I have a PC, a server, a laptop. On the left and on the right I have the same PC, server and a laptop. These devices, they will connect to our network, to the switches. These switches, they usually layer 2 switches, one of the cheapest switches or less capable switches. Because all the need for these switches is not to do a really fast switching. For them it's just to be able to have enough ports for us to connect the end devices. Now this layer, the switches that work on this layer, they're called access layer switches. There's no connection between those switches together. They don't connect to each other, they do connect to another layer, which is the distribution layer. Okay, the capabilities of these switches, what they should be able to do is just layer 2 switching. They're not concerned with layer 3 devices or anything. Well, they don't even understand layer 3 switching. They are high availability. We need to have lots of ports and have high availability. Port security, we can implement port security on those switches. Well, the port security, for example, is if the switch will have a MAC address of the PC that is meant to connect to that port, to one port. If another PC is trying to connect to the same port, the switch will disable the port. Well, it will shut it down. There will be a violation there. In this layer or access layer, we can implement quality of service, classification and marking, and trust boundaries. We can mark data that comes from PC, server or laptop. They have a better priority than other packets or other frames, I should say. Then we move on to these switches. They do address resolution protocol inspection. For address resolution protocol or ARP inspection. Then on this layer or access layer we can implement virtual access control list, and we implement the spanning tree on this layer as well. These switches or layer 2 switches, they can have something called power over Ethernet as well. Power over Ethernet is we can power some of the devices they need electricity, like IP phones for example. So those switches to connect, they connect directly to the distribution layer. The next layer is called the distribution layer. Now these switches on the distribution layer, they are better performance than access layer switches. They are layer 3 to see. You can see it from the icon. They have a different icon because this is a layer 2 switch. It can't perform layer 3. For example, you can't understand routing, or we can't go to the individual port and give it an IP address. These are just layer 2 switches and they work in access layer. Distribution layer switches, they are layer 3 switches. In here what we do is, first of all, we have a connection to the access layer, and we can do routing for the network. So aggregation of LAN and or WAN links, routing services between LAN and VLANs, and between routing domains, for example EIGRP to OSPF and so on. And these switches, they perform redundancy and load balancing. Now the third layer is core layer. Well, the core layer, these switches, they don't meant to do any routing or anything. Their job, the main job, is to do really fast switching. So switch of the data very fast as possible. Okay, now Cisco recommends this 3-layer hierarchy to implement on your networks because it's easy to, for example, for modularity, for scalability, it works very well. Now we can, for example, scale in this network very easy. We can troubleshoot this network very easy. So we don't, if we, for example, put PCs in the core layer, now when something goes on in our network, we don't really know what switch to go and start troubleshooting. If it's separated like this on 3 layers, it's a lot easier for troubleshooting as well. Now some companies, they can't implement 3 layers because maybe it's too expensive. So what they can do is something called collapsed layers, collapsed 2 layers. So they will still have the access layer like we always do, but the core and distribution layer will be like only in 1 layer. So core and distribution will be just 1 layer. So it's 2-layer hierarchy. Moving on, form factors. We know the form factors, the switches will have a different kind of form factors. Like PCs, for example, form factor for PC will be tower or desktop. Tower PC, desktop PC. Well, same for the switches, they have their own form factors. First kind of form factor is fixed platform. With the fixed platform, the switches are just the way that you buy them. You can't enhance them. You can't buy extra ports here and add them as you need them. So you can't use, if you buy, for example, 12 ports or 24 port switch, that's it. You're stuck with that 24 port switch. You can't increase, you can't remove one of these and add more ports, or for example. Fixed configuration switches do not support features or options beyond those that originally came with the switch, which is true. You can't enhance extra features from what you have purchased. Then we have a modular platforms. With the modular platforms, is more for high-end businesses because these switches, they will have modules. In the modules, if you need, for example, extra 24 ports, you just buy another module, you add it in the switch, and that will give you an extra 24 ports. Which means these here are modules. On top of it, with these switches, they will have a redundancy power. For example, you can't see it very well, but down here there are 2 power supplies. So in case one of them fails, the other one will take over. So modular configuration switches offer more flexibility in their configuration. The last type of form factors is stackable platform. On the stackable platform is if you want to add more than one switch to add it, for example, to increase the port density in your switch, we can stack them together. Well, we can stack these switches together if you use one of these ports, like we use port from here goes to this port, kind of like we are making 2 switches, but they will work individual. They will not like they will start even competing between each other for spanning tree elections and so on. If it's stackable, what we do, we implement this cable, this special cable that's gonna stack those switches together, and even though we put 4 switches together here, they will behave like 1 switch. So it's only 1 configuration for the switch. So stackable configuration switches can be interconnected using a special cable that provides high bandwidth throughput. Now, some of the switches, they are not stackable capable. So you have to check at the back of the switch if it says stackable. Then you will know that that switch can be stacked. Some of the switches, like old switches, they don't allow you to stack them. So form factors depends on the cost first. The cost of a switch will depend on the number and speed of the interfaces, support features, and expansions capabilities. So these are the difference between the form factors. Then we can look at the port density. Network switches must support the appropriate number of devices on the network, which is true. If you have 48 PCs that you want to connect them to the switch, you don't go and buy the 8-port switch because there's not going to be enough ports. So you just need whatever devices you need to connect, or you need a switch that has enough ports in there. Power. It is now common to power access points, IP phones, and even compact switches over using power over Ethernet. This is a great feature because you don't have to buy an extra or plug an extra power outlet for the IP phones. The switch will provide the power. In addition to power over Ethernet consideration, some chassis-based switches supports redundant power supplies. reliability, the switches should provide continuous access to the network, which is true. They should be very reliable. If we look at the port speed, the speed of the network connection is one of the primary concerns of the end users. So obviously the end users, they're going to start complaining if the switch is slow. Frame buffers, the ability of the switch to store frame is important in a network where there may be congested ports to server or other areas on the network. And then the last form factors that we have to think of is scalability. The number of users on the network typically grows over the time. Therefore, the switch should provide the opportunity for the growth. Frame forwarding, the fundamentals concept of switching, refers to a device making a decision based on two criteria. This is how the switch forwards one of the frames it receives. Well, it looks at the ingress port, the port that the frame is coming in, and the destination, where the frame is trying to go. So as a frame comes in, for example on this port, the switch will mark what is the MAC address the frame is coming from, and it looks at the destination address, EA for example, looks at the port table which has the destination addresses with a port. So it will look at that, do I have EA on my port table? It will find out that EA is on port 4, and it will move this frame from port 1 to port 4. That's called switching from one port to another port. Well, how do the switches populate that table, that MAC address table? For example, I have a switch here that has 4 ports, port 1, port 2, port 3, and port 4. For example, now the switch has this MAC address table that it's empty. It knows nothing. So the switch is waiting for them to receive frames. Imagine there's a PC here that we have with the MAC address AA. Now you have to remember the MAC addresses are 48 bits and they are represented in hexadecimal numbers. But just for me not writing 48 letters here and numbers, I want to write just abbreviated to AA. Imagine this PC has got MAC address AA. Now this PC is sending a frame to another PC called the MAC address BB. So AA is the source, BB is the destination. As the frame goes into the switch, what the switch is going to do first is going to say, okay, well I just received a frame from port 2 and the source address is AA. So let me write that down on my MAC address table. So it writes down, okay, it says port 2, I got frame with AA, MAC address AA. Destination was BB, but it looks at the MAC address table, it doesn't see BB anywhere. So when it doesn't know what to do with that frame, what it's going to do, the switch, is something known as flooding, which the switch is going to flood that frame to every port, port 1, port 3, and port 4 in this case, apart from the port they came in. So we're not going to send it to port 2. And hope that it's going to reach destination. Now let's imagine that BB is on the other side and it's got that frame. So what it's going to do is going to reply. Source address BB and destination is AA. So as a frame goes to the switch, what the switch is going to do, it says, okay, well, I just learned where BB is. BB is in port 3. So I'm going to write that down on my MAC address table. So port 3 is BB. Okay, done that. Now I look at destination. Where is it going? It's going to AA. Do I know where AA is? Yes, I do. It's on port 2. So I'm going to send it to just port 2. I'm not going to flood it, or I'm not going to send it to every port. So that's how the switch learns is a MAC address table, well, relation to MAC address table to the port numbers. And if a device sends for example, broadcast is all Fs, FF, 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 and so on, all Fs. The switch will always behave, it will always do the flooding. It will always behave like a hub. It will flood it to every port apart from the port it came in. So if this was the destination, was a broadcast address, the switch will flood it. So switching forwarding methods, we have two methods. First of all is store and forward. This method makes a forwarding decision on a frame after it has received the entire frame, and it's checked the frame for the errors. So first it receives the whole frame, stores it in the memory, checks for the errors, and then it makes a forwarding decision. The second method is cut through. This method begins forwarding process as soon as it reads the destination MAC address of the incoming frame. So storing forward, for example, as when the frame comes into the switch will first check for frame for the errors. Well, store in the memory, check for the errors, perform automatic buffering, and then this type of the method is, well, if forwarded then, but this type is very slow because the switch is storing all the frames in the memory before it starts forwarding them. But it's very safe because it's going to check for the errors, so making sure that there's no errors on the frame. The second method is cut through, which we talked about. As soon as the frame comes into the switch, sorry, that gone too fast. As soon as the frame comes to the switch will make the decision really quickly in less than 10 microseconds, and as they will not do a frame check sequence and no automatic buffering. This method is really fast, as you can see, because it's only checking the destination MAC address. And now we talk about collision domains, different type of collision domains. First of all, a hub. A collision domain in the segment where devices must compete. All ports of the hub belong to the same collision domain. For example, I have a hub here. This hub has got 4 ports, similar to the switch earlier that you saw. Port 1, port 2, port 3, and port 4. The hub, it's all ports on the hub are in one collision domain, which means that if one device sends one data, the other device, if it sends the data at the same time, there will be a collision, which means only one device can send or receive at the time. So all other devices, they have to wait for that device to finish transmitting. This is not very good because there could be a lot of collisions in the network. If there's a collision, they have to wait for random backoff timer until they start sending the data again. So remember, that's the icon of the hub as well. So I want you to pay attention to that icon, and it's one collision domain, hub. On the switch, in this case, I'm going to change this hub to switch. This is the icon for the switch now. Now you have to see that statement there. Every port of a switch is a collision domain on its own, which means that if this device sends some data, there's not going to be a collision here because this link is only for this device, but it's still considered as one collision domain. This switch with this PC here is a second collision domain, and this switch and the PC on this side on the port 4 is a third collision domain, and 4 collision domains. So here we have 4 collision domains. You have to remember, every port on the switch, well, every active port on the switch is its own collision domain. But switch is still a part of one broadcast domain, which means that if one device sends a message, for example, if this device sends a broadcast message, every device on the network will hear. Imagine if we have like 100 or 200 devices or 1000 devices on this network. One broadcast, everybody will hear it. All the PCs. To break the broadcast domain, we implement the router. Now the router, every port on the router is its own broadcast domain. So as you can see here, this router's got 2 ports. That will be 2 broadcast domains. So I want you to stop the video and think, how many broadcast domains and collision domains do you see on this network? Okay, stop the video, calculate it on a piece of paper, write it down, and then start the video again. We'll go through it. Okay, in this, first we look at how many collision domains. We have 1 collision domain here. That's a switch. Every port, every active port on the switch is its own collision. So 1 collision domain. This is the second collision domain. Then we have another collision domain here between the router and switch. So that's our third collision domain. 1 more here on this side on the right between the switch and the router. 4th collision domain. Between the switch and the PC, that's a 5th collision domain. 6 between switch and the PC here. And the last one is the seventh, is between the switch and the hub. So the hub is one collision domain in the hub. So every port on the switch, every active port, it's its own collision domain. Hub, in the other case, all the ports are in one collision domain. What about broadcast domains? Well, that's one broadcast domain on this side and another broadcast domain on this side. So two broadcast domains.